All right, so let's talk about half-life here. We got a couple of videos coming up that will explain the problems, but now let's just talk about half-life in general. So if you look at this graph, let's figure out what's going on. We've got two curves. We've got one going down and one going up. The down one shows the parent isotope. So if you notice, it's less and less and less. And if we pay attention to the numbers, the units here are percent. So we've got 100% of our isotope to begin with at time 0. So when x is 0, when time is 0, no half-lives have passed, we've got 100%. But now one half-life has passed. Now we don't exactly know how many years this is or how many minutes or how many seconds because we don't even know what isotope this is, but we know the generic time frame, which is one half-life. And a half-life is defined as the amount of time it takes for half to decay. So whatever your sample is, half of it is going to decay in that time period. So if we start with 100%, we're going to be down to 50% after one half-life right there. And then after another half-life has passed, 1 to 2, now we're down to half of 50, which is 25. And then we're down to half of 25, which is 12.5. And it keeps going like this, on and on and on, as we get closer to 0. Now, the rule is after about 10 half-lives, you pretty much have 0 left. It keeps getting closer and closer and closer to 0, and then eventually we pretty much have nothing left after about 10 half-lives. So the dark curve here is showing the parent. This is what you start with. This is the unstable parent that's going to turn into these more stable daughter products. So as one is going down, the other one's going up. So we can look at this in two ways. Here's my isotope that's unstable. After one half-life, it goes down to 50%, and the other one started at 0, the daughter, the more stable isotope, and it went up to 50%. And then after another half-life, the parent goes down to 25. After another time period has passed, now we only have 25, but the stable one went up to 75. And eventually we're going to end up with 100% stable and pretty much 0 of our parent isotope as it keeps decaying and decaying and decaying. So what you need to know from this is half-life is a certain time period. We don't know exactly what this is, so we have to look it up. And after that time period goes by, for whatever isotope we have, we only have half of that sample, and then half, and then half. This is kind of like if you took a whole bunch of pennies and you put them in a box and they're all heads. After one flip, you can assume that half are going to flip and become tails. So let's say you put 100 in, after one flip, you probably have about 50. If you put 200 in, after one flip, you have about 100 that are tails, and so forth. And then after another, you shake it and another half life goes by. Now half of that sample. So if you started with 100, it's going to go to 50, and then it's going to go to 25 are going to be tails. If you started with 200, now you've got 100 that are tails, now you've got 50 that are tails. So it keeps cutting itself in half because you have basically a 50-50 shot of flipping your coin here and landing on the tail side. Over here, each isotope has a 50-50 shot of decay. So maybe this guy does decay, maybe this guy doesn't. It's always got a half of a chance to decay within that half-life. Just like your pennies have a half of a chance of flipping, 50% chance of flipping every time you shake it. Now, if we look at this screen here, we see that there's a list of just a few of these isotopes, and you look at their half-lives, and they range from minutes all the way up to years. Look at uranium's half-life. Uranium-235, 0.7 times 10 to the 9th years. No wonder we have problems with radioactive waste. You look at carbon-14, 5,730. So if you start off with 100% carbon, something that's living, after about 5,730 years, it's only going to have 50%. So if it has died, carbon-14, if it's died and then 5,730 years pass, now it's going to go from 100% only down to 50%. So if we have numbers, let's say it had 28 grams of carbon-14, and then after 5,730 years after it's died, now we're going to be down to 14 grams of carbon. That's kind of high, but you can still imagine the numbers would work it this way. Even if we have 28 milligrams, it would be down to 14 milligrams. And then after another 5,730 years goes by, now 14 is down to 7 grams. So if you measure something and it's living, you would expect to see this mass. If you measure something and it's only got 7 grams, now you know a lot of time has passed, basically 2 half-lives. So then you multiply 5,730 years times 2, and you know how old it is, if it's only got 7. And look at some of these other ones. Some of these have a half-life that's measured in days. Like bismuth, 5 days go by. So if you have 28 grams of bismuth and 5 days passes, now you have 14. Another 5 days, and now you have 7, and so forth. So now you know to get from 28 to 7, 10 days must have passed. So we can use this half-life to figure out how old things are. We can use it to figure out how long it's going to take before it completely decays. We can figure out with some values to start with how long it's going to take to get down to a certain amount, and so forth. So we're going to look at some problems dealing with half-life in a couple minutes. But the big idea here is that every time one of these half-life passes, your nuclei has decayed, half of your nuclei have decayed, your daughter isotopes have been formed, and it keeps cutting in half. So basically you take out a calculator and just keep hitting divided by 2, divided by 2, divided by 2, divided by 2, and every time you do that, one of these half-lives have passed.